Welcome back. In today's problem, we want to use the phasor technique to simplify each of the following expressions into a single term. Let's start with v1 of t. So we're going to call that 1. And we see that we have a difference of sinusoids. We can apply the sum or difference formulas or trig identities, but then again, we can just go ahead and convert that to the phasor domain and then manipulate from there. So our first property we're going to use is that x of t equals a cosine of omega t plus theta in the phasor domain is equal to a times the complex exponential e to the j theta. So then v1 of t is equal to 12 times the complex exponential e to the j 30 minus 60 times the complex exponential e to the j minus 45. From here, we can then apply Euler's identity, which is e to the j theta, which is equal to cosine theta plus j sine theta. This now, our expression simplifies to 12 cosine 30 plus j sine 30 minus 6 sine 45 plus j again. So we forgot our j. So we should have our j 6 sine of 45. My bad. So you can list the cosine or the sine first, but so that's why I forgot. I thought I should have put a j in. So that should have just been 6 cosine of 45 plus j 6 sine of 45. We can then go ahead and add our cosines together, factor out the j, and add our sines together. This then simplifies to 6.15 plus j and 10.24. Here, we can then apply our properties from complex algebra. We have this is in rectangular form. To get to polar form and then to the time domain, we use the following properties. So our first property is that a is equal to plus or minus x squared plus y squared. And then our angle theta is equal to the inverse tangent of y divided by x. And in polar form, we have the following, and we're dealing with x, so let's just use x times the complex exponential e to the j theta, and then we can just change our a to the following. So by applying those rules, we then end up with 11.95 times the complex exponential e to the j 59 degrees. And then we can then go ahead and reuse the first property, which allows us to convert from time to phasor or phasor to time. So now we're going from phasor to time. So a is now 11.95, and we have cosine omega t. Omega t in this case is 6t plus an angle of 59 degrees. So that's v1 of t in a single term. So we can then attack v2 of t. We can change both our sign to a positive cosine and then evaluate. So the first thing we do to change a sign to a positive cosine, we use the identity. So cosine of x is equal to plus or minus sine of x plus or minus 90. We can then go ahead and change our sign. So our negative 3 sine is going to change to 3 cosine, we're going to use omega t, and then minus 15 plus 95 gives us a angle of 75. We're going to change the minus 6 to a positive minus 6 sign to a positive cos 6 cosine omega t, and positive 15 plus 90 gives us 105. Then we can just rewrite our 12 cosine omega t, and I think that's minus 60. So here we went from a 3 sine to a 3 cosine by using the identity. So in minus sine, we add 90 here, minus sine, we add 90, and rewrite the following term. So, second portion of that is just basically applying the phasor and time domain relationship. So then we can go to the phasor domain, and that's going to be 3 times the complex exponential e to the j 75 plus 6 times the same thing, changing the angle, 12 with a minus j 60. So we can then apply Euler's identity, which we have here, to this expression, and then add. So not going to write that out. What I'll do, let's just walk you through that. So from each of these terms, we know we're going to get a cosine. So we can then go ahead and add cosine 375. So 3 times cosine 75, 6 times cosine 105, and we can add 12 times cosine of 60. So that will then give us 5.2235, or just 5.22. Then we can go ahead and factor out the j, because all of these terms are going to give us a j sine 75, j sine 105, and a minus j 60. So the coefficients are included as well. So we factor out the j, and it's going to end up to be a positive. So a 3 times sine of 75 plus 6 times sine of 105 minus 12 sine of 60. So that simplifies to 1.70. Here again, we apply our complex algebra properties, and then we go to polar form, which is 5.49, and that's 5.4929. We just stop at 49 times the complex exponential. Here we have an angle of negative 18.02 degrees. Now we're in the phasor domain. We then use our relationship, phasor to time domain, and convert back to the time domain. So we keep our a, so that's 5.49 times a cosine of omega t. In this case, omega t was 1,000 times t. So you could write a 10 to the 3 or whatever you want to write, times t, and minus a 18.0 degrees. So this is V2 of t. And here we express V2 of t into a single term. We then can go on and do V3 of t, which, so the first one we've done, we did not convert our minus cosine to a positive cosine. So let's do it for this one. So this is 3. So that is going to, so let's write our trigonometric identity first. So in our case here, we can say that cosine of x is equal to minus cosine of x plus or minus 180 degrees. So that means V3 of t is going to then simplify 2. So we keep the first term in the expression, 2 cosine, and let's replace 377 times t as omega t and a positive 60 angle. So our negative 2 cosine is changed to a positive 2 cosine with an angle of 180 added to the minus 60. So we then end up with 120. So here, to change it to a positive cosine, we add 180, and this goes down to 120, change over to a positive cosine. So we can then go ahead and apply. There's going to be another formula. We might not use it as yet, but let's just change this to the phasor domain as always. 2 times e times the complex exponential, 2 times e, so that would be a, which is 2, so 2 times the complex exponential e to the j 60 plus 2 times e to the j 120. We then go ahead from there and go into rectangular form by using Euler's identity. And as always, we know what we're going to get when we convert to Euler's, when we use Euler form to convert to rectangular form. Euler's identity to convert to rectangular form. So we can go ahead and add a 2 cosine 60 to 2 cosine 60 plus 2 cosine 120. That gives us 0. And then we can go ahead and j times 2 times the sum of sine 60 plus sine 120 gives us 3. So that's j. So that gives us 3.4641. So we can round that to 46. We need to use the identity that j is equal to e to the j pi over 2, or just 90 degrees. By using that, we can then go ahead and write that as 3.46 times e to the complex exponential j90. That simplifies too by using our time domain to phasor domain. That simplifies to 3.46 times cosine omega t, and then plus 90 degrees. However, cosine of 90, without even looking at the identity, if we have cosine in red and we shift that a positive 90 degrees, we delay. So in this case, we delay, so advance. So if you shift it positive, we advance it. So it would be in, so let's put that in black. So that means we advance cosine, a positive angle shifted to the left and a negative shifted to the right. So if we advance, as you can see, if we advance our cosine that was in red 90 degrees, a positive 90 degrees, then it shifts to the left by 90 degrees, and now it becomes a cosine. So this is then equal to, so v of t is then equal to a minus sign, because by the way, this is not a positive sign, this is a minus sign, because if you remember, a positive sign is of this form. So that's a minus sign, and we keep our coefficient, so 3.46 times sine, and omega t is 377 times t. And that is the single term for v3 of t. So we can then go and simplify the last expression, which is the easiest, I would say. So let's do that. So that expression, so let's call that, is that 4? So let's call that 4. So the first identity we're going to use is our cosine identity, which we have here. I'm going to use this identity to convert. So let's get that going. So the first thing we do is then convert our sine to a cosine. So let's write our identity down. So cosine of x is equal to plus or minus sine of x plus 90 degrees. And that's plus or minus 90. V4 of t, V4 of t, here V4 of t, we see we have a sine, so that's where we're converting that to a positive cosine. So that's going to equal, we keep the first term, so that's 10 times cosine omega t plus, now we convert our sign, so we have a positive sign, so we subtract 90. Positive sign, subtract 90. So it's going to be 10 cosine of not x, omega t, minus 90 degrees. We can then convert that to the phasor domain, and we're using our time domain to phasor domain relationship as always. So it's e to the j, and we're just going to put 0 in this case because we don't have any angle for the first term, plus 10 times the complex exponential e to the j, and that's a minus 90. We can then go ahead and apply Euler's identity, but before you do that, you can just say this is going to simplify, and let's just do it the right way. So cosine, so 10 times cosine of 0 will end up with 1, plus j times, so j times 10 times sine of 0, then we go ahead and plus 10 times, so that would be 10 times cosine of 90, end up with a 0, minus a j times 10 of sine of 90, we end up with a 1. So all that simplifies down to 10 minus j times 10. Here we have our expression in rectangular form. We apply the complex algebra identities to get to the polar form. So in polar form, that equals to 10 times the square root of 2 times the complex exponential e to the j minus 45. And now we just use the time domain relationship, the time domain to phasor domain relationship, and we end up with a v of t is equal to 10 times the positive square root of 2 cosine, and our omega t was 800 times t, and we end up with an angle of negative 45. So that's how we simplify our expressions from the time domain into a single term by converting back and forth. So we convert to the phasor and to the time domain. While in the phasor domain, it allows us to add or subtract or divide or multiply easier than if we should keep our cosine and sines in the time domain. So that's it for today's video. I'll see you in the next one. Bye.